Okay, this is the equations. We go into sketching. Y equals to x squared minus x minus 2 over x squared. Looks pretty complicated. So we're going to do a few steps, and then we put all these features on the curve, and I'm going to show you how you look like. So first feature we're going to do is finding the vertical asymptotes. Step 1. To find the vertical asymptotes is we pretty much using the domain, which is x is not equal to 0, the denominator. We're using the denominator cannot equal to 0, and the asymptote would be, we call the VA, vertical asymptote is x equals to 0, which means x cannot equal to 0. That's your asymptotes. X cannot touch that, zeros. Okay, first step done. Second step, we're finding horizontal asymptotes. So how we find the horizontal asymptotes? The meaning of horizontal asymptotes is the function will be approach a certain line when the x approach to infinities. So let's do these limits. So we do limit when x approach to infinity, very big x values. What is your y approach to? So let's do these limits. So to able to get the limits of this rational function, we usually go divide by highest power of x on both numerator and denominator to make equivalent fractions. So in this question here, your highest power is x squared. So I'm going to divide by x squared everywhere. So that's still making equivalent fractions. Okay, and then because we're making a fraction like this, so first one is 1 minus 1 over x minus 2 over x squared. And then you go 1 on denominator. And then you can see when x approaches infinity, so this one becomes 0 and this one becomes 0 because any number over infinity is a 0. So then in the end, we left with 1 minus 0 minus 0 over 1, which equals to 1. So therefore your horizontal asymptote, I write as HA, y is equals to 1. Okay, second step done. They are the features of the curve. So third step, usually we go is the x-intercept and y-intercept. So we let y equals to 0. So original function is that. So when y equal to 0, meaning x squared minus x minus 2 over x squared equal to 0. Then we remove denominator by times denominator x squared on each side. So give me x squared minus x minus 2 equal to 0. And we factorize into x minus 2 and x plus 1 equal to 0. So therefore, x equals to 2, or x equals to -1. So it looks like we're going to have 2 x-intercept, which is 2, 0, -1, 0. Good. And then the next step is the y-intercept. So y-intercept is at x equal to 0. So with the original function this, again, So I'll make x equal to 0. So I have y is equals to 0 minus 2 over 0 square. You can see a big problem I created, which is I made the denominator 0. That is impossible for any math functions. So therefore, no y-intercept, because x cannot equal to 0. So it's a big feature here, no y-intercepts. All right, good. Step 4. So we are going to finding our stationary points by doing the derivative. So original function is y equals to x squared minus x minus 2 over x. So to able to the derivative of this, looks like we are going to using quotient rule because we have numerator and the denominator. But to avoid using quotient, most people don't like quotient, it looks very complicated. We can do some tricks here. Look, we can split the numerator by doing x squared over x squared minus x over x squared minus 2 over x squared. So it makes the whole fraction into 3 terms. First term become 1, second term become 1 over x, last term become 2 over x squared. So now we can derivative separate each term by first changing them into index looking. So this one become x to the power of negative 1 and this one become 2 x to the power of negative 2. Alright, now it's ready to derivative. So I'm going to do derivative dy dx equals to 1 derivative is going to be 0 and x to the power of negative derivative become negative going down, become positive x to the power of negative 1 minus 1 get a negative 2. And next one going to have negative 2 times negative 2 going down and x to the power of negative 2 minus 1 negative 3. So I'm going to tidy this up, become 1 over x squared plus 4 over x to the power of 3. So first derivative done. And then we do for a stationary point. I'm going to let dy dx equal to 0. So I have 1 over x squared plus 4 over x cubed equal to 0. And then to able to solve this equation, as you can see, we have denominator x squared and x cubed. I'm going to remove denominator by multiply x cubed every term. So the first term become x. Second term become just 4. And the 0 times x cubed still going to be 0. So therefore, I find my station point is x equal to negative 4. And then I'm going to sub it into the x equal negative 4 back into my original function, which is here again to find my y values. So y will be equals to negative 4 to the power of 2 minus negative 4 minus 2 all over negative 4 squared, which gives me 16 plus 4 minus 2 over 16. And then do the simple calculation will give me 9 over 8. Okay, so therefore, stationary point at negative 4 and then 9 over 8. Whew, long process. Next step is we have to determine the nature of the stationary point. So what I'm going to do is I'm going to use second derivative. So I'm finding the second derivative here. Okay, and in the first derivative, which is this one here. And I do one more derivative. which is x to the power of -2 plus 4 to the power 4 times x to the -3 and all derivative, which equals to -2 x to the power of -3, then minus 4 times 3. Why is minus? Because I'm times -3, and the x to the power of -4. So that's my second derivative. So now I'm going to sub in my station point x equal to -4 into the second derivative. So that gives me equals to -2 times -4 to the power of -3 minus 12 times -4 to the power of -4, which gives me -1/64, which is less than 0. Therefore, is concave down, gives me that stationary point is a maximum turning point. Okay, that's really determine the shape of my curve. That's a big features for the curve. Right, okay, next one is I'm going to find my inflection point. So I'm going to do, this is step 4, and we're going to do step 5. Inflection point. So we let second derivative equal to 0. So my second derivative was -2 x to the power of -3 minus 12 x to the power of -4. So equal to 0. Then let's see. So I'm going to change back into a normal fractions, makes it easy for you. Okay, so it's a -2 over x cubed minus 12 over x4 equal to 0. Again, I'm going to remove my denominator by times x to the power 4 on each side, which gives me -2x, -12, and the 0 times x4 still 0. So that's good. So then I got my inflection point, x equals to 6. -6, yes. So then, but that's only give me a possible point of inflection. I have to check concavity change. By drawing the table values around the x equal -4 to see the second derivative, if it changes the sign, then I see if it does change concavity. And if it does change, it means an inflection point. If doesn't, then it's not an inflection point. So let's check. So I'm gonna using two numbers. So I'm gonna use -7 and -5 around the possible inflection points. So I know at -6, the second derivative will be equal to 0. So at -7, I sub a -7 into my second derivative, which gives me big fractions, 2 over 2401, and the -5 give me -2 over 625. Okay, so I can see, so here is concave up, and here is 0, and here give me concave down. It does concavity changed. So then we can say Therefore, when x equals to -4 and y equals to -6, x equals -6, y equals to 10/9. That's right, 10/9. Yeah, that point is a point of inflections. Okay, almost done. Last step to go. With the horizontal asymptotes, we have to test for my horizontal asymptotes. So you're probably wondering, what do we test for horizontal asymptote for? As you notice, when we're finding the horizontal asymptotes, long way back, is here. So is when x approach to infinity, which is with a very big x value, the curve will approach to this line here. But we don't know when the x is not very big, would it be curve and the asymptote actually they cross each other. So that's what we test for now. Test for the horizontal asymptotes. We test for this. So now let's see if they cut each other. So we do simultaneous equations with the original function y equals to x squared minus x minus 2 over x squared. And with my horizontal asymptote is y equals to 1. So we simultaneous equations. We sub equation 2 into the equation 1, so it gives me 1 is equals to x squared minus x minus 2 over x squared. Remove denominator again times x squared on each side, give me x squared equals to x squared minus x minus 2. So I have cancel the x squared, therefore I have x is equal to -2. So it does cut y is always equal to 1 at x equals to -2 here. So this is the point when the horizontal asymptotes and the curve intersect. And we only finding one point, meaning we only cutting once. And the rest of the curve don't touch the horizontal asymptotes again. So it's a good features for this curve. So I think now it is for me ready to sketch. So I'm gonna put all these features back into the curve. So let's go back to revise all these things. First things, vertical asymptotes. Okay, I'm gonna use different colors. Red, vertical asymptotes. And the second one, horizontal asymptotes. I'm going to using purple here. Y equals to 1. And the third one is intercepts. I'm gonna using blue. So I have the x-intercepts and the no y-intercepts, which means don't touch the y-axis. And the next one, I think it was my stationary point. I'm gonna using this, let's say orange. Stationary point is at here, but I box here because you can see this is a maximum turning point. Okay, and the next one I'm going using the green inflection point, and it's here. I'm going to label all of these things. And then last one where the horizontal asymptotes and my curve cutting each other at this point. Let's say the blue. All these features are going to show you on my curve. Right, let's sketch. It's very interesting. I'm going to draw my number plane, which is hopefully fits here, x-axis, and my y-axis here. Okay, orange here, and then first one was the vertical asymptotes, red, can see a lot of it. Second one is horizontal asymptotes. I think it was purple at x equal to 1. Let's make this is 1 here. And the next one was the intercepts. I think it was this navy blue. So I have two x-intercepts at 2 and at -1. -1, two x-intercepts. Nice. And then no y-intercepts, so I don't have to worry that. -1. Okay, and then next one, let's go stationary point. I think was orange. I have one maximum turning point at -4. Let's go. -2, -3, -4. And the y was 9/8, which is a little bit above the line here. Let's make here. That's my station maximum turning point, which is -4, 9/8. Okay, good. And then next one, I think is my inflection points. Green is at -6, which is here, -6, and the y value is 10/9. I think is a little bit less than my stationary point. Let's just say here. Okay, that's my inflection points. I write my inflection points here. 10/9. Wow, very colorful, interesting. And then what's my last thing? I guess was the blue is where it cuts the horizontal asymptote. Interesting. People say, oh, asymptotes, you can't not touching it, but we actually find a point where it does cutting. It's at -2. Which is here, and 1, it cuts. How does it goes? Okay, it cuts. But we still gonna approach the line with no touching later on when x very big. But when x not very big, such as -2, you do cut. Last thing, I'm gonna put my curve there. Let's go. Since I have my x-intercepts here and not touching the horizontal asymptote anywhere else, so I'm going to do here, and the vertical asymptote is going to be very close here, not touching, vertical asymptote not touching. And then here, I'm gonna join all these colorful dots together and same time using my vertical asymptotes, not touching this. Okay, which way should I go first? Okay, I think I go this way, and it's very close to here. Maximum turning points. Okay, let's carefully go. So this is concave up. After the points become concave down with my maximum turning points, and I'm touching my cutting points here. And then my x-intercepts here. And then last thing is your vertical asymptotes. Very close, but not touching. Nice. It's to be smooth, not wonky. Nice, smooth. Showing all the features. That's the shape of my curve. Beautiful. Done.